Okay, we'll revise the first aspect of control design, that is nominal stability and performance. So we had seen 9 maps, and we had seen the conditions for Weibull stability of all the 9 maps. So it boiled down to make sure that 3 of the maps, that is pk by 1 plus pk, p by 1 plus pk, and k by 1 plus pk, are Weibull stable. So a new definition is of roots and of the zeros and poles of a transfer function. So zeros of a transfer function is basically the roots of the numerator. So if a transfer function has been represented in terms of numerator by denominator, where numerator and denominator are polynomials in S, so zeros are the roots of the numerator and poles are the roots of the denominator, and hence each map can be represented in terms of uh, zeros and poles of transfer functions P and S. Now we'll start the first aspect, that is nominal stability and performance. So nominal stability is to make sure that each map is bistable, and we had seen that that boils down to make sure 3 of the maps are bistable. Now nominal performance is to make sure that the given map uh, follows certain criterias and requirements. So first is of reference tracking. So we need to make sure that the our output tracks the reference, and hence we had in terms of step response, it the mapping should have low overshoot, low settling time, and low rise time. So we had seen the case of second order system, and we had seen the result that a choice of zeta between zero point 0.6 to zero point 0.7 acts as a good balance. So we'll see that through this curves. So this is the step input, the black curve, and an ideal output should be of no overshoot, no rise time, and settling time. But the second order system give these curves for a constant value of omega n and varying zeta. So we see that zero point 0.6 to zero point 0.7 does a good job as compared to the lower values in tracking the curve. So in Bode plot representation, reference tracking can be represented in terms of the dB magnitudes and phase use as the black curve. So we want the output to input ratio to be 1. So in dB magnitudes that translates to 0 dB, and we want the phase no phase difference, and hence the phase should also be 0. But now comes the problem of reference tracking, the trade-off between reference tracking and noise rejection. So we see that uh, the coefficients of the map R2y, R2y and N2y are both same, just the signs are different, and hence uh, both simultaneously reference tracking and noise rejection may not seem possible. But there's a solution to this. So physics suggests that the frequencies of noise are usually high due to the physics of working between atoms and molecules and working of a sensor, and hence so this is what we require. We want the reference to have 0 dB magnitude, but we want the noise to have very small magnitudes. So hence we can choose a reference such that they are smaller as compared to noise sensor noise, and hence we first track the reference and reject the noise. So we reject the high frequency noise and track the low frequency reference. So that translates to this green line, and we see that general second order system do a good job in following this, since they almost track the 0 dB for low frequencies and heavily attenuate the high frequency sensor noise. So again, this is to revise that for sensor noise rejection we would want the magnitudes to be 0 and hence this to be 0. So but this is similar to the reference tracking. This was the ideal curve if the sensor noise have high frequencies and the reference have low frequency. Also in phase, in since our references would be chosen for low frequency, we want the phase also to be 0 initially, and after that we don't really have to analyze, since the magnitude it's themselves would be smaller, hence the effect of phase would be small. So yeah, this is the first aspect. We'll continue in the other video. Thank you.